Our definition yesterday was that instead of looking at the sum as a whole, we look at the partial sum and then consider the sequence of partial sums. If that converges, whatever that limit is, we're going to call that the total of our series. And as long as I am adding positive terms, then I have a monotone sequence. It's increasing. If I can find an upper limit bound, and I know it's monotone, the sequence must converge. So the question is, what sequences converge to things I can figure out easily? Because the hardest of all possible things is to try and figure out a nice version of this. That's going to suck. So hopefully, I'll be in a position where I can look at series and the sequence of corresponding partial sums and find patterns. We talked about a geometric sequence. What was that? So we start with some number, and in my sequence, I started with 1. And I multiply by r. So I have r, and I have another r, so I get r squared, another r, and I get r cubed. Well, I can actually do that starting with any number. But this time, I'm going to add a twist. I want to look at a geometric series. A geometric series is a sum where each piece in the series, each term, is geometrically related to the one in front of it. So this starts with an a, and then an a times an r, and then an a times an r squared, and then an a times an r cubed, and keeps going. Now, I've written that with our index starting at 1. That's why the power is r to the n minus 1 up there. Because I want the first one to have no r's at all. And then the second one has 1 r, and the third one has 2 r's. That's why that's 1 less. But I've seen this before. This right here, this is a geometric series. This looks like this. If I think of A as being 1/2 and R is what I multiply to get from each term to the next, is also 1/2. So that sequence of, that series illustrated by my box is actually an example of a geometric series. But it could be any ratio R, the ratio between consecutive terms. So somebody pick a number. Yeah? Any number. Okay. So if I let A equal 2, somebody else give me another number. 13. That's going to get really big really quick, isn't it? Right? So I would have the sum of a r to the n minus 1, n equals 1 to infinity, would look like 2 plus 2 times 13 plus 2 times 13 squared plus 2 times 13 cubed, and so on. Yes? I'm going to run a hunch here. I continue to add bigger and bigger and bigger and bigger numbers. What do you think is going to happen? That should diverge. Should. Huh. This. I think this format up here, this way of writing a geometric series, AR squared, I think that's my key to figuring out a way to add these up. Let's look at a partial sum. That would be, you know what? I used n up there. So I'm going to change this from a little n to a capital N. That way I can tell the n's apart. Sum n equals 1 to capital N, AR to the n minus 1. So this is AR squared, AR cubed, all the way up to AR to the capital N. So I have S capital N can be written out R to the 1, AR squared, AR cubed, AR to the capital N. My problem is that my first reaction is that I don't know what that should add up to. This is a 1 up here, or you can just eliminate it altogether. There shouldn't be an exponent on that. The trick I am about to show you is almost 300 years old at this point. I'm going to take this sequence, this series, this partial sum. I'm going to multiply it by something. I'm going to multiply it by R. What do I get if I multiply that by R? Not only do I want you to write that down, I want you to line stuff up by powers of R. So I would multiply this by an R. That would be AR. I would multiply this by an R. That would be AR squared. This times R would give me AR cubed. There's one right in front of here, isn't there? That would be AR to the capital N minus 1. But I multiply an extra R in there. I get AR to the capital N. And then when I multiply this, I get AR to the N plus 1. Ready for the sneaky part? Subtract. If you subtract, what happens over here on the right-hand side? But wait, more than just those three. Everything except the first one here and the last one here has a matching partner, right? So all of those terms in the middle will cancel out. The only thing that's left is an A and a negative AR to the capital N plus 1. Now on the left, I have S capital N minus R S capital N. As long as R is not 1, this worked. Why is R being equal to 1 a problem? So this would be A and A and A and A, and the top would just have N, and the bottom would just have N. Oops. that doesn't do me much good, does it? N minus N is 0. So as long as R is not 1, this actually gives me stuff. There's an Sm on both of these terms. Oh, and on the right-hand side, there's an A in both of those terms. Holy crap, wait a minute, look at this. I have a formula for Sn. As long as R is not 1, I can divide. I believe that this particular trick is either attributed to Carl Friedrich Gauss or to Leonhard Euler, both mathematicians of the late 1700s. I found an expression for my partial sum. Yes, and that means now I can ask, how does this thing work? Right? Because I want to know if the partial sum has a limit. I want to know what happens to this as n goes off to infinity. Yes. That was my problem, is that I used the small n earlier, so I made it a capital N. If you don't like that, change this to a K and that to a little n. You can use whatever symbols you like. Okay. The only thing that changes as n changes is this number right here. And that means that it's r to the n plus 1 that I need to figure out. Wait a second. I know the answer to that. I know what happens when I repeatedly raise a number to a bigger and bigger power. We made a number line, didn't we? Find the number line from yesterday. Hold that thought. People are still looking and flipping. I want more people to find this. What number line information did we come up with about R? As a matter of fact, a bunch of you gave me the same number. I asked you to draw on our number line. Leo, what did we decide? Right, but what number did we decide were the important numbers that mattered here on my number line? Aha. If we were outside of -1 and +1, we went off to infinity. If we were on this side, we ended up over there after we squared, and then we went back and forth, but we kept getting bigger. If we were in between -1 and 1, we went to 0. R to the n plus 1 goes to 0 if and only if R is between -1 and 1. Otherwise, R to the n plus 1 diverges. Well, that allows me to figure out my limit. Limit as capital N goes to infinity, write that capital N correctly, please, of S capital N is the limit as capital N goes to infinity, A1 plus R to the capital N plus 1 over 1 minus R. That's what Sn is. And we know that this goes to 0 only when we are less than 1 in absolute value. So if the absolute value of r is less than 1, then r to the n plus 1 goes to 0. Whoa. Hang on a second here. The top, this piece will be a 0, so the top will be a times 1. The bottom will be 1 minus r. I just get a over. That's a limit. That's well defined. That works as long as r is absolute value less than 1. If that's the case, a geometric series will converge. I just found a formula that will allow me to add up an infinite number of things in 1 second. Provided the things I am adding are a geometric series. Oh, okay, wait a second. We said that could be written with a equal to 1/2 and r equal to 1/2. One half times a half, 1/2 times 1/2 squared, 1/2 times 1/2 cubed. Let's apply our formula. Our formula says a over 1 minus r. What's the denominator of that fraction? And that makes that 1/2 over 1/2. And isn't that what we got yesterday? Son of a randy-legged bandersnatch, it worked. Because I got a sum. It converges. It goes to a finite real number. Diverges means either the limit doesn't exist or it blows up to infinity. That's not infinity, and that exists. You're still looking at me like I've done something very sour.
Well, in the top started a times 1 plus r to the capital N plus 1, and now it's a times r to the little n minus 1.
This was the partial sum. The series itself looked like this, ar to the n minus 1. Dominic.
What does
A is our initial value, our starting term. In this case, it was the first number, the 1/2. So here's another one. Yeah, that's my reaction too, Madison. Oh, geez, what the is this? No. We can get here. We can get here. I want to try and write this as A R to the n minus 1. Now, if I'm doing that, then this should be A, this should be AR, this should be AR squared, this should be AR cubed, and so on, right? If I'm right, and this is geometric, it needs to match that pattern. So, assuming I am correct, A should be 5. And if that's the case, what's the value of R? Say again? Almost. Say it again. Negative 2/3, because notice the signs keep changing. And I can do that by saying, oh, negative 10/3 over 5 is negative 2/3, and that's AR over A, so that should be R. Oh, if I'm right, what's negative 2/3 squared? Say again? And if I multiply that by 5, I get 20 over 9, and it should be positive because I squared my negative. If I multiply by 2/3 again, the top gets multiplied by 2, that becomes a 40, and it changes to negative. The bottom gets multiplied by 3. Yeah, this looks like it's right, which means that this sum is 5 negative 2/3 to the n minus 1. N goes from 1 to infinity. Madison, do you see how I made it AR to the n minus 1? Wonderful, brilliant, I love it. What is the value of the absolute value of R? So that means that the absolute value is less than 1. And that tells me, Maddie, that it's convergent. That's exactly what I can do. The total sum is A over 1 minus R. I can add up infinitely many numbers right now. All I have to do is do that. A over 1 minus R.
So you're not using the absolute value.
No, this is R itself. The absolute value is only used to determine whether or not it will converge. One minus a negative becomes 1 plus, so the denominator is 5/3. 5 over 5/3, take the 5/3 out, turn it over, and I get 3/5 times 5, which is, Leo, 3. There we go. I have performed infinitely many additions. It took us all of a minute. Excuse me while I cackle evilly. The power. Now, it is often useful to write series that have variables in them. Please notice I have changed the N to an I. Big deal. I don't care what letter you call it. What's the value of A in that series? 1. And R is my X, right? Now, since X is a variable, this is only going to converge for some X's. But when it converges, what's its total? Unfortunately, no. If this converges, I want to use this formula again. So I'm going to put in A. We said A was 1. 1 minus R. Remember when I started talking about this stuff for the exam last Friday? I said that this stuff came before derivatives and before limits, really. We were looking at adding sums up. I can define a function using a sum. Before we were ever doing function notation, we were defining functions as series that looked kind of geometric. By the way, these are called power series. And we will talk about them in more detail later. But this is just our taste of things to come. Power series actually turn out to be absolutely hugely important. And I can tell you right now, the three of us would be blind as bats without them. Power series design classes. But that's later. I just want to note for a moment that the way I write my series can change. Compare those two to each other. The one on the left is the one we were just looking at, our power series. The one on the right is the same thing. Huh? I made a substitution. N is equal to I minus 1. Now, just like with U substitution, pass your limit through that equation. If I is equal to 1, what's N? It would be. So my lower limit changed. But my upper limit is infinity, and infinity minus 1 is still infinite. So I really only had to change the bottom one. This is called re-indexing. I'm sorry? Because sometimes it is more convenient not to have that minus 1 up there. Yes. But now I have what looks like a different series. The first problem we did with the 1/2, the first time I encountered that problem, I saw it like this. And then my formula looks different, doesn't it? It's not n minus 1 anymore, is it? But this is now starting at 0, so this is still the same total. So the question is, do you want to see an nth power, or do you want to see an n minus first power? Because you're going to get the same formula, you just have to look at what your index is. This does come up later on again when we start looking at other series. I promise there's a use for this. Yeah. Well, yeah, but since I'm subtracting one, the substitution actually went the other way. But I can start a series wherever I want. I can start it at 1, I can start it at 17, I can start it at 13. The total changes unless it's a geometric series. And then it's got to match one of these two forms to use this sum. Now, the reason I bring this up is sometimes it takes a little work to make it look right. This is a geometric series. And most of the time when I say that, at least one person's face in the room is going, like hell it is. That does not look anything like a geometric series, does it? Because geometric series either looks like this, or it looks like AR to the n minus 1. And this doesn't look like either of those. So what the hell? This is starting at 1. If this is starting at 1, geometric should start with AR to the n minus 1. Those are the two formulas for geometric series. So I need to make this look like this. Ladies and gentlemen, there is a bunch of algebra ahead. That's all it is. It's algebra. I don't like that. Especially not when I want n minus 1 for a power. This is 1 minus n. It's the wrong way around. It's the negative of n minus 1, isn't it? Oh, so I could, instead of writing this as 3 to the 1 minus n, I could write it as 3 to the negative n minus 1. But wait, there's more. Negative powers. Where did negative powers go? They go to the denominator. So let's take that 3 to the negative n minus 1 and make it 1 over 3 to the n minus 1. I'm getting warmer. If I do that, then it won't be something to the n minus 1. But now I have to look at the 2's. How do I deal with the 2's? 2 times n. I have a power that has multiplication in it. There was a rule about multiplying powers. If I'm multiplying, then I add the powers. But here, I've already got the powers and they're being multiplied. It is. It's the power of a power. So instead of writing 2 to the 2n, I'm going to write that as 2 to the 2 to the n. What's inside the parentheses? 4. So that's just 4 to the n. I like that. But it would be nicer if it was an n minus 1. Yeah?
If you want to divide the numerator, divide it by 3 to the n minus 1.
It would be nicer if that was an n minus 1 power to match the n minus 1 power in the denominator. So I want to do something before I put it on top. You said if I'm multiplying, then I'm adding powers, right? So what if I took 1, 4 and left the rest of them over there? Because n minus 1 plus 1 is n. I can add the powers. Isn't that a sneaky pain in the ass thing to do? Now, instead of putting the whole thing on top, just put the 4 to the n minus 1 on top. And that leaves a single 4 out in front. Now, why would I do such a psychotic thing? I have the same power on top and on bottom. I can put that whole thing in parentheses and make that r to the n minus 1. It's the right form, yay! Now what?
My r would be 4/3 and my a would be a fourth.
That is correct. But before we go ahead and plug into our formula, what do I notice about that r? Greater than 1, that means that that actually diverges. I can stop right here. Stop. R equals 4/3 is bigger than 1. This diverges. So I don't even bother to put it into the formula. This turned out to be geometric. And I could identify that that would blow up and give me something that doesn't make sense as a total. Either the limit keeps bouncing back and forth, or it eventually becomes infinity. And since this number is getting bigger, each term should be getting bigger, this is going to blow up. Aha! Nope, I just know that it doesn't converge, I'm done. All right. I want to steal other ideas that we've already used. Here is a series that is not geometric. Clearly, that is not geometric. 1 over n times n plus 1. Not a geometric series, I'm not multiplying by the same thing over and over and over again. So I have to go back to the drawing board. And I have to say, I need to know what the partial sum looks like. I don't like this very much. But I say to myself, that thing that I am adding up looks like something I did back in chapter 7. It looks like a factored denominator. Say the magic words. Chapter 7, Section 4. Partial fractions. Now, I'm going to go ahead and give it to you, but I expect that you would be able to do the work to come up with A and B. In this case, both A and B turn out to be 1. So I cheated and I picked one that I rigged and didn't advance, and I'll just give it to you for now. So that means that this series really looks like that. At this point, my brain usually goes, but that's not any nicer. That still sucks. Let's look at a partial sum. S capital N is going to start with 1 over 1 plus 1 over 2. That's when n equals 1. Oh, wait a second. Typo. Typo. A equals B equals -1. Doesn't help if I write the damn thing down wrong. What goes in the next set of parentheses? This is where n equals 1. This is where n equals 2. What fractions go in here?
It would be 1/2 plus 1/3.
Oh, except it would be,
-1/3.
aha, so 1/2 minus 1/3. And then the next one is 1/3 minus 1/4. And I keep going. Until I get to the last one. Because remember, this is a partial sum, so it ends at capital N. What wonderful thing do you notice that's going to happen? A Pirates of the Caribbean moment. I promise. There's a Jack Sparrow moment right here.
You're not allowed to see things that can't interact with it.
Not just the last two.
But the 1/2, 1/3 is up the 1 and -1.
In other words, this collapses on itself. And the only thing that survives is the first number and the last number. Gee, that sounds familiar. My Jack Sparrow moment. Here I am in the crow's nest with my telescope, and this giant thing, one segment after the other, collapsed down like a telescope being put away. As a matter of fact, this is called a telescoping sum. And telescoping sums only come from partial fractions. Or something that is already expressed in this sort of subtraction form. Now, what is the limit as capital N goes off to infinity? No. I can only get telescoping using this sort of partial fraction sum. What happens as capital N goes off to infinity? That's going to be 0, which means the limit as n goes to infinity of Sn is 1. Okay, one more example, and then a couple of important theorems need to be mentioned. Example. Remember our harmonic sequence? 1 plus a half plus a third plus a fourth. Well, the harmonic series is the sum 1 over n. 1 plus 1 half plus 1 third plus 1 fourth, and so on. It turns out that this diverges. And there is actually a very nice proof of this divergence in the textbook. But I'm going to give you the quick and dirty version. If you look at the first term, you get 1, right? Instead of doing the partial sums in groups of one more thing, I'm going to group more at a time. If I add both of those, that's at 1.5, right? If I add both of those, that's bigger than 2. Why do I know that? Yeah.
It's like 1.5 plus.
Ah.
Plus a fourth, so it makes it bigger than 2.
Those two put together are bigger than a half, aren't they? Those two is a half, and a half. Oh, sorry, 2 halves. So that's 4 halves. That's too big. If I do the next 4 numbers, that set of parentheses there on the end, that's bigger than a half. Because that's an eighth, an eighth, an eighth, and an eighth would give me a half, and those numbers are bigger than an eighth. So that means that if I add up the 1, that's 5 halves, isn't it? That's bigger than 5 over 2. If I take the next 8 numbers, 1 over 9, 1 over 10, 1 over 11, all the way up to 1 over 16, that's bigger than a half. That gives me 6 over 2. I add the next 16 numbers of adding in powers of 2, aren't I? No matter how far out, I can make this as big as I want. This diverges. Now that actually turns out to give rise to a very amusing problem in physics. Or, if you would rather, in construction. I have a challenge for you. Not a big challenge, just a little challenge. I'm going to give you a stack of identical coins. I only have 2 with me at the moment, but you can have as many as you want. I want you to stack them, not one directly on top of the other, but I want you to offset them slightly. My question to you is, how far over can you go with the top coin? You're not allowed, you don't have to stack them one on top of the other. You can move them off to the side a little. So your coins could be stacked like this. And notice that the top coin is further to the right. My question to you is, if you make the stack as big as you want, how far do you think you can go? You think you could get the top coin actually off the bottom coin? Do you think you could get it way over here? Well, it turns out the center of mass of my stack of coins obeys the harmonic series, which means you can move that top coin as far to the right as you want. This particular result is from 1955, the Leaning Tower of Lira coins from Italy. And do you see the picture? There's 1/2 unit there, there's 1/3 unit there, 1/4, 1/5. That's the harmonic series, exactly as I wanted it. You could do it with Legos too, if you didn't click them together, if you just kind of stacked them on the smooth sides. You could make a bridge that went as far over as you want without ever actually clicking them together. Okay, Some important results of the thesis of series. If my sum is convergent, then the individual terms go to zero. You can't have terms getting bigger and bigger and bigger and have it add up to something finite. The reverse of this is more important. If the limit of my terms is not zero, then my sum diverges. We're going to use this one a lot. I call it the test for divergence. We can add series, we can subtract series. We can multiply series by numbers just like they were functions. And we will use that manipulation on our series as we move forward. My goal in the long run is to try and figure out, here's the series. Does it converge or does it diverge? And then I'll start looking at power series and where they converge and diverge. And that's where I'll show you why I'm not blind, because of how series make glasses. But that is not for today. Tomorrow is question and answer day for 11.1 and 11.2. It's taken me 3 days to get through 2 sections. So I will see you tomorrow for question and answer. Have a wonderful rest of your day. I did post the Leaning Tower of Lyra paper to our Canvas webpage.